Okay, before we talk about motion, kinematics, we need to distinguish between scalars and vectors. So in physics, there are two types of quantities. Those that have a magnitude or a number or a value associated with them but no direction, and those are called scalars. And things that have a direction associated with them are called vectors. So distance is a number. Distance doesn't have a direction. If we put a distance with a direction, we call it displacement. So we're going to distinguish between distance, which is a scalar, and displacement, which is a vector. And in a few minutes, I'll define this term displacement. Speed is a scalar. It's the distance covered over the time it takes to travel that distance. I'll write that down later. Speed is never negative, but velocity is the speed at any instant and the direction the object is moving. And so we need to specify the speed and the direction. We have a vector, we call it velocity. So when we say speed, we're talking about a scalar with no direction. Velocity is a vector. The rate at which velocity changes, I'll define that in a minute, is acceleration. That's also a vector, so acceleration has a direction. And force has a direction, and momentum has a direction. So these are the three vectors that you'll see this semester. The 5 vectors you'll see this semester, and here are the 3 that we'll be talking about this week. Some other scalars like time doesn't have direction, mass doesn't have direction, energy doesn't have direction, and temperature doesn't have direction. So these are other examples of scalars, but for this week we'll just be talking about these 3: distance, speed, and time. Okay. When you look at the equation sheet posted on Moodle, you'll see under one-dimensional kinematics there are 2 groups of equations, and the first group is this group, and this group is our equations of definition and also equations that we'll use to solve problems, but the main function of these equations are defining terms. So in physics, definitions are often equations. So let's go to the first term, displacement. This is the equation, but I'm going to read it to you and I'm going to say it in a different way. So delta x equals x final minus x initial. But the other way to say it, the more complete way to say it, is the displacement of any object is its final position, is the initial position subtracted from the final position. And so you'll be doing, whenever you're calculating the displacement, you always find the location of the final position and the location of the initial position. And if you're on, like many of the exercises, if you're on a straight x-axis line, if the final position is a smaller number than the initial position, then the displacement will be negative. So if you imagine this line and you're here at position 25 and you go to position 5, then the initial position was 25, the final position was 5, and so 5 minus 25 is a negative 20. So that means 20 units of displacement in the negative direction. So that's the directional quality of displacement, is distinguished by a plus and minus sign for this week. Now, once we have displacement, we can find average velocity. So the average velocity is the total displacement divided by the time interval it takes. So you go from some initial position to some final position over some period of time. And usually t initial is 0, but if t initial were 10 seconds and t final were 20 seconds, then the time interval would be 10 seconds. So this is how we calculate average velocity. But in the case of an object that's changing velocity, like a ball rolling down an incline, right? If a ball rolls down an incline, it's speeding up. And so if we calculate its average velocity, that doesn't tell us anything about the instantaneous velocity. Just like if you drive 30 miles in a half an hour, then you're going 60 miles an hour, but at any instant in time, you're probably going a different speed or velocity. So to get the instantaneous velocity, it is distance over time, but to actually measure it, we have to measure a small distance in a small time. To get it exactly, right? So if you wanted to know how fast a car was going and you timed how long it took to go 100 meters, you'd get a certain value. If you timed how long it took to go 10 meters, you'd get a better value. If you timed how long it went 1 meter, you'd have even a better value of the velocity at that instant. And so the way to think about this is to measure a velocity at an instant in time, you have to measure a distance and a time that are very small, ideally vanishingly small. And so this is a calculus concept. You'll recognize this unless you're in Calc 1, maybe you haven't gotten to it yet, that if you take the limit as delta t approaches 0 of this ratio, of this division, you get the derivative. And the dx just means a vanishingly small delta x over a vanishingly small time interval. So the best definition of velocity uses calculus. It's the derivative of the displacement vector over time. Okay, now we want to know how the velocity changes, so we define acceleration, and the average acceleration then is going to be the change in velocity over the change in time. And so if you wanted to know how much something accelerated, say a car starts from rest and accelerates, you want to know the velocity in the beginning. In this case, it would be 0. And then the velocity at the end, and how long it took to go from the beginning velocity to the end velocity. When you divide it by the time, you'll get something. I should have put down the units here. Let me just write down units. I'll pause for a second. Okay, so generally we'll measure velocity in meters, in some cases centimeters, and then we'll get, oh no, I made a mistake. Okay, so displacement will be measured in meters, and velocity, whether it's average or instantaneous, will be meters per second. And acceleration then is meters per second, like how many meters per second the velocity changes per second of time. But meters per second, we usually write it as meters per second squared. And so when we get to acceleration, if we just take a final velocity initial and divide it by the time, we get the average acceleration. But if we want the acceleration in an instant, we have to do the same thing we did here. We have to take the change in velocity over a short time interval, ideally a very, very short time interval, an infinitesimally small time interval, and then we get the derivative delta v delta t. But since v already is a derivative, you get, for those of you that have had Calc 1, you get dv dt is the second derivative of the displacement vector with respect to time, and it's written this way. So acceleration is either the first derivative of the velocity or the second derivative of the position vector with respect to time. And in either case, the units are meters per second, or equivalently meters per second squared. Okay, let's put these terms and concepts to work. So here's a flat inclined plane, and we have a ball rolling down the ramp, and it goes 1 meter, 100 centimeters, and it takes 5 seconds. And you can see from the motion diagram, I'm showing you the position of the ball at every second as it goes down the ramp. Clearly it's speeding up. And so what I would like you to do is to calculate the displacement, the average velocity, the instantaneous velocity at the end, and the average acceleration. So if you think you can do that, pause the video and do as much of that as you can. You can back up and listen to what I asked you to do. If you can't, I'll be back to show you how to do it. Okay, it's all kind of crowded together, but the displacement, of course, is the final position, and I didn't mark these, so this is position 0. I marked it now. This is position. We actually have these tracks in the lab, and they're marked off in centimeters with 100 centimeter marks. They're actually 120 centimeters. And we have a frictionless cart that rolls down the ramp like the ball. We'd actually do this in lab if we were on campus. So also 5 seconds, if you imagine, that's a long time to go 1 meter. So that means the angle is very, very small. So another thing to keep in mind is, and the tracks that we have can be adjusted, if the angle is 0, the acceleration will be 0. Except for friction, the cart would just go at a constant speed. And as we tip it up, the acceleration gets bigger and bigger. So the steeper angle's going to go down faster. So generally in lab, we do angles between 2 degrees and 8 degrees, and we get times between 2.5 seconds and about 1.5 seconds. So 5 seconds would be a small angle, maybe like 1 degree of angle. Anyway, so the displacement's 100 centimeters, the final position minus the initial. We divide that by the time interval, 5 seconds, and we get an average velocity of 20 centimeters per second, right? It's averaging 20 centimeters every second. It goes for 5 seconds. It goes 100 centimeters. But clearly, the initial velocity is 0. So I'll write that here, because it started from rest. We released it from rest, so V initial equals 0 centimeters per second. And if the average is 20, then logically the final velocity should be double. And that's based on the concept that the average velocity could also be calculated by taking the final velocity, the initial velocity, adding them together and dividing by 2. Just like you would get the average of 2 exams. If you got 100 on one exam and you didn't take the second exam and you got a 0, your average for the 2 exams would be 50. So this is another useful equation that's not included up here in these equations. And so if I multiply both sides by 2, I get V final plus V initial equals 2V average, and V initial 0. So I get the equation that V final is twice the average, 40. That's what we expected, right? If it starts at 0 and it averages 20, it should end at 40. So let me write that down. V final equals 40 centimeters per second. Not writing very well. And now we can calculate the acceleration. I didn't write the equation, but the acceleration is V final minus V initial over the time interval. So 40 centimeters minus 0 centimeters, V final minus V initial over the time interval, 5 seconds. means it's averaging 8 centimeters per second per second. So this is the velocity we're talking about. So now notice, it starts at 0. After 1 second, it's going 8 centimeters per second. After 2 seconds, it's going, say, at 16 centimeters per second. After 3 seconds, it's going 24. Then another 8, 24, 32, 40. So you see the velocity increases steadily. It's getting faster at a steady pace. So the average acceleration is constant, and so that means the acceleration at any instant is the same as that. It's always, at every point, 8 centimeters per second. So I won't bother to write that down, but just go through that again, right? The velocity here is 0, 8, 16, 24, 32, 40. And you can imagine when you do the graphing equations how you would graph that, what that graph would look like. Now we want to get the positions. So there's an equation in the second set of equations that I haven't showed you yet for getting the position. But I'm going to show you a way in which we can get it with the information we have. So this starts at 0. And it gets here, it's going to be 8 centimeters per second. Maybe I can write those numbers in. I'll just pause and write them in. Okay, so watch how I come up with these numbers. Between 0 and 8, the average here would be 4, right? During the first second, the average would be 4. So in the first second, it goes 4 centimeters. Now, if we go over 2 seconds, so this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, it's speeding up. The distance is getting bigger and bigger. So at this position, it's 4 centimeters. Now, when it goes from here to here, it's going from 0 to 16. So over this interval, it's averaging 8. And so that's averaging 8 for 2 seconds. This would be 16. So let me write that down. I won't remember these. So this is at 4 centimeters. This is at 16 centimeters. Now in the third second, it goes from 0 to 24. From 0 to 24, that's an average of 12, but that's over 3 seconds. So 12 times 3 is 36 centimeters. So after 3 seconds, it's down here. At 4 seconds, the instantaneous velocity at 4 seconds is 32. That means from 0 to 32, it's averaging 16 times 4. This is 64 centimeters. And then between 0 and 40, it's averaging 20. Oh, we already know that. All right? And it's averaging 20 for 5 seconds, so it's at 100 centimeters. So these are the positions of the ball every second, and this is called a motion diagram. And it's a nice way of visualizing the motion. You can easily see that it's an accelerated motion going down the ramp, and there's a lot of problems in the Minds on Physics problems like this. They're called oil drop problems, right? Okay, next. Okay, last thing I want to mention is if you go to your equation sheet, you'll see first these 5 equations, and then following them you'll see these 4. So these 4 equations are called the equations of motion or the kinematics equations, and these are the equations that 9 times out of 10 you will use to solve problems. Occasionally you might use this one, but notice if we go up here to this equation and we write the t final minus t initial as delta t, and instead of writing delta t, I'm just going to write t. So by rearranging this equation, we get v final equals v initial plus the acceleration times the time. You could rewrite this, right? And if you would get, if you subtracted v initial and divided by time, you'd get v final minus v initial over time equals acceleration. So this is just a rewrite of this equation for average acceleration. And so these equations are good. These equations are good under the conditions the acceleration is constant. Then the average equals the instantaneous because the acceleration is not changing. Now the next equation is a rewrite of this one. Remember we said that, and it's only true for constant acceleration, strictly speaking, that v average is v final plus v initial over 2. So if we take v average and multiply by the time, that's how we get the displacement. That's how we get these displacements in this diagram. So this is called equation 2. We give these equation numbers. We use these equations a lot. You'll use them all semester this course, and you'll also use them throughout the course in second semester physics. So these are very widely used equations. Now, from these two, we can derive these two. So these are convenience equations. If we didn't have these, we could still use these two equations, but these make it easier to solve problems. So notice that in this problem, in this equation, there's no v final. So this equation is useful. Supposing we know v initial, it's 0. Supposing we know the acceleration and the time, we can calculate the distance. So this equation we use a lot. And notice that v final is missing. So you see v final here. If we take this, which is v final, and substitute it in here for v final, try doing the algebra, you'll come up with this equation. And notice this equation is another useful equation because it doesn't have time in it, because sometimes we don't know the time. So you'll see many situations where we want to use this equation because we can't measure or we don't know the time. And so if I take this equation and I take this equation and solve it for time. So in this equation, time would be equal to, watch this, v final minus v initial divided by a. So if we take v final minus v initial divided by a and substitute it here for the time, and then do the algebra of this equation, you'll end up with this one. If you like doing algebra, try doing that. So these are our kinematics equations. I'll refer to them by numbers. And they're good in any situation where the velocity is constant. Okay, one final thing before signing off on this video. Notice I have 4 different ramps. I have a straight ramp at a low angle. I have a straight ramp at a higher angle. I have a ramp that curves this way, and I have a ramp that curves this way. And notice the difference. So if this ball rolls down, it's going to take longer and have less acceleration than this ball because this is steeper. This will get down faster and it'll accelerate more. But in both cases, since the angle is constant, the acceleration's constant, right? Because bigger angle means bigger acceleration. If the angle is constant, the acceleration will be constant. But here the angle's varying. So this one starts out with a big acceleration, it'll get going very fast, but near the end, even though it's going fast, it's not going to change here where it's flat. So this will have a high acceleration here, and as the angle gets lower and lower, and here it'll be going very fast, but the acceleration is 0. Here, the acceleration in the beginning is going to be very small. Then as the angle gets bigger, the velocity is increasing, and so is the acceleration, until it reaches a maximum value where the slope is maximum. So these two tracks have accelerations which aren't constant. You would not be able to use these equations in the case of these problems. But as you'll see, almost all the problems we do in first and second semester physics are situations where the acceleration's constant. Okay, we're done for now.